Alright, we've got a couple of interesting topics for today. The first is equipotential surfaces, or sometimes we look at equipotential lines. And the other is the electric field determined from the electric potential. I mentioned in the previous video that we were going to do that. This makes life a lot easier sometimes. Starting out with equipotential lines or surfaces, those are the green dashed lines in this image here, and they are what the name implies, locations where the potential is constant, hence the name equipotential. And one way to identify them is that equipotentials are always perpendicular to the E field. And if you think about what's going on there, if you're moving perpendicular to the E field, there is no force needed to move because the E field indicates the direction of the force. So if you're moving perpendicular to that, it takes no force. If there's no force, there's no work done, and if there's no work done, there's no change in potential energy. So that's one way to kind of get at this idea of an equipotential. They don't have to be zero. These equipotentials here have different values. Everywhere along this first dashed line is 5 volts, and the middle dashed line is 10 and 15 and so forth. We can also learn from this idea that the surface of a conductor, regardless of the shape, is always an equipotential because, as we talked about earlier, the field lines always go perpendicularly outward from the surface of a conductor. And as we just said, perpendicular to the E field gives us an equipotential surface. Let's look at the equipotentials due to a point charge. In that case, we know that the closeness of the field lines indicates the magnitude. So right here is going to be an equipotential because the E field is constant through that region, and pointing outward is the E field, so we make circles that are perpendicular to those lines pointing outward. You can draw any circle that is centered on the point charge and it will be an equipotential surface. Once again, the values of those equipotentials can change, but pretty straightforward. We can get a little bit more complicated situations if we have more charges around. Our equipotentials don't have to form straight lines or nice perfect circles. They can curve as our electric field lines curve. As long as our equipotentials are always perpendicular, we can get some different shapes going on there. Just to draw an analogy to gravitational potential, this quantity that we don't really look at, but if you have a topographical map where each of these lines represents a given elevation, those lines also represent equipotentials for gravitational potential energy. Alright, that's basically all there is for equipotentials. Let's get to E determined from V. So we've previously seen this expression here. We've defined our change in potential in terms of this integral here. Well, if we take the derivative of both sides of these things, then the integral goes away on this side and we get the derivative of the potential, and then we swap sides here and we don't forget our negative sign. So we can get our electric field in terms of the rate of change of our potential with distance. So when we write it in terms of L, we're just talking about any distance in any direction, but often we want to break that down into components. So we can find the x component of the electric field by taking the partial derivative of our potential with respect to x, the y component with respect to y, and so forth. Partial derivatives, I believe we mentioned those last semester. They are not really any more complicated than regular derivatives. You just take the derivative with respect to this variable, and you treat any other variables that might be present as constants. And so it doesn't really make it any more complicated. It just makes you look smart because you get to use these funky curly symbols here. Alright, let's look at a couple of examples of doing that. So here is the potential due to a ring of charge, which we derived in the last equation, in the last video. Came straight from this equation here. It wasn't too difficult to derive. In the last unit, we derived the electric field due to a ring of charge, and this was kind of a pain in the butt to derive. We had to do it with Coulomb's law. This is one of the situations I mentioned where it's not really easy to derive the electric field with Gauss's law. You're not going to find some nice symmetric Gaussian surface that gives you a shortcut like you would for a line of charge. So we want to get from this guy to that guy using our new expression. So E equals the derivative, the negative derivative, of our potential, and the electric field is just in the x direction, so that's all we're going to be concerned about is dv dx. Now the k and the q are constant, so those we can pull out, it doesn't really matter, and then we're going to have d by dx of 1 over x squared plus r squared. And you guys could throw that on your calculator. We'll go ahead and work through it. It's really not that bad. Derivatives tend to be quite a bit easier than integrals. So moving right along here, I find it's easier to think about these derivatives if we move things up into the numerator. So we've got x squared plus r squared. I forgot my negative sign. Ripley would be not pleased. This is going to be to the negative 1/2 power if we bring it up here. Now I'm going to jump over here to continue. The negative kq just comes along for the ride. If we bring that negative 1/2 power down, like we do with our good old power rule for derivatives, then this becomes x squared minus r squared, and we have to subtract 1. So negative 1/2 minus 1 is going to give us negative 3/2. Then we still have to take the derivative of the inside. The derivative of r squared is 0, and then the derivative of x squared is going to give us a factor of 2x. We can cancel out that 2 with the 1/2. We can make our negatives a positive, and what we're left over with is kq. I've still got an x up top here, and we're going to go ahead and put this back down in the denominator. And lo and behold, guess what? It worked. We got our E field quite a bit more simply, I would say, than finding it directly. One more example. So now if we want to find the electric field due to a disk of charge from the potential, this is our potential that we found in the last video. And this is the electric field. We've actually derived this in that other video, even though most of the time we simplified it to sigma over 2 epsilon naught, under the assumption that r was much bigger than x, because in that case this just becomes r squared because the x squared goes away, and then you have r squared to the 1/2, which is just x over r, and since r is bigger, then this whole thing just goes to 0. So this is a simplification we used a bit, but we want to rederive the whole big nasty thing, starting with this guy here. First thing I'm going to do is I'm going to adjust these constants out in front so that it looks similar. So instead of k, we can write 4 pi epsilon naught. And then I've still got my r naught squared. I can make that a 2. And q over pi r squared, so this guy and this guy, that's q over area, and that's the definition of sigma. So this whole thing becomes sigma over 2 epsilon naught, which is just what we have over there. Alright, so continuing on from there, we're going to take the derivative. We want to find E, which is negative dv dx, just squeezing everything in here, because why not? D by dx, squeezing in again, of x squared plus r squared to the 1/2 power minus x. You could probably go ahead and end now, unless you really enjoy watching people do derivatives, but I'm going to do it because, you know, it's fun. Alright, so sigma, I got my negative there, 2 epsilon naught. We can take the derivatives of each of these two terms separately because that's how it works, and life is easier that way. So, alright, we're going to pull down this 1/2, and we're going to have x squared plus r squared to the negative 1/2 power, because we subtract 1 from the exponent. Then we multiply by the derivative of the inside, which is again 2x, minus the derivative of x, which is going to give us 1. And then if I get rid of that and distribute this negative through, then guess what we're going to get? Yes, the right answer. So that negative 1 becomes a positive 1, then I end up subtracting this thing. I've got an x up top. I'm going to put that in the bottom, and voila, we have our nice, wonderful expression for the electric field due to a disk of charge. Even if we are very close, or sorry, very far away, this equation here still works. Okay, that's all. See you next time.